If you take a piece of plastic and hold it against a refrigerator door, it falls right to the floor. But take a small piece of iron and it slaps right onto the metal, holding its own weight against gravity. We describe this through the lens of magnetic fields, but the observable field is really just the final effect of a much deeper, more complex engine operating at the atomic scale. Zooming into the iron atoms of the magnet reveals a landscape where classical physics no longer applies. Down here, particles follow a logic that contradicts our everyday experience of how objects should behave. The strength of that magnet is actually generated by an invisible quantum mechanism known as exchange interaction energy. This interaction acts as a silent architect for much of the physical world. It governs the behavior of household magnets, the stability of chemical structures, and even the immense pressures that prevent dead stars from collapsing under their own weight. Imagine two identical cars driving down a highway side by side. You can easily tell them apart because one occupies the left lane and the other occupies the right lane. But subatomic particles, like electrons, do not work like solid cars. They act like blurry clouds of probability. And when two electrons get close to each other, those physical clouds start to overlap. This document details indistinguishability. It points out that when these electron clouds overlap, the physical universe entirely loses the ability to tell them apart. If you swap their positions, absolutely nothing about the system changes. Because these particles have no separate identity, the underlying math of the universe has to actively manage what happens when their identical probability clouds mix. To solve this, the universe forces an incredibly strict set of personal space rules on these particles. The strict law governing this microscopic personal space is called the Pauli Exclusion Principle. It states that no two electrons can ever occupy the exact same quantum state. A quantum state is defined by a combination of two things: an electron's physical location and the direction it's spinning, called up or down. When two of those blurry electron clouds wander into the same space, they are forced to negotiate, and the resulting energy of their interaction is decided entirely by which way they are spinning. First, consider the anti-parallel scenario, where one electron spins up and the other spins down. Because their spins are different, their quantum states are different. The Pauli rule is satisfied, allowing their physical clouds to heavily overlap. But there is a massive penalty for doing this. Forcing two negative electric charges to share the same tight space creates intense electrical repulsion. This leaves the system in a highly stressed, high-energy state. Now, look at the parallel scenario, where both electrons are spinning in the exact same direction. Because their spins are identical, the rules say they absolutely cannot share the same physical space. The universe steps in and forces their probability clouds to spread out and avoid each other. Because they are physically kept further apart, the electrical repulsion between those two negative charges drops significantly. The result is a much calmer, lower energy state. If you calculate the mathematical difference in energy between those two setups, the high-stress overlap versus the relaxed separation, you get the exchange energy. It is an energy gap that exists for one single reason. The universe has to balance its budget to handle the paradox of identical, indistinguishable particles. Which brings us right back to that piece of iron clinging to your refrigerator door. Iron behaves as a ferromagnet because its internal exchange interaction heavily favors that lower energy setup. It aggressively encourages its internal electrons to adopt parallel, aligned spins. As this text explains, when you force billions of these tiny electron magnets to line up and face the exact same way, their individual microforces combine. They merge to create the single, massive magnetic field you feel in your hands. And this energy sorting rule scales well beyond simple metals. When atoms share electrons to form covalent chemical bonds, the exchange interaction dictates their exact arrangement. It decides whether atoms stick together to build a water molecule or repel each other completely. You can track this rule into the most extreme environments in the universe, the super dense cores of dead stars, like white dwarfs. When a star exhausts its fuel, gravity tries to crush it inward, but that crush forces electrons so close together that the Pauli Exclusion Principle triggers a massive outward push, a cosmic phenomenon known as degeneracy pressure. That exact same invisible repulsion, electrons refusing to share the same quantum state, generates a force strong enough to completely halt the crushing weight of gravity. It is the only thing keeping the star from compressing into a black hole. Our physical reality is built on a bizarre accounting trick. From the magnetic field holding your notes to the fridge, to the structural integrity of a star, everything holds together simply because the universe has to keep identical particles in check.